Today I want to discuss the thesis that I've been outlining in the last couple of episodes about self-learning, self-supervised reinforcement learning, the need to develop better animation tools in order to enable self-supervised reinforcement learning. I think I'm going to use this episode to outline a strategy and in fact also open up the communication to the outside. So whoever's listening to this and has an interesting business model or an interesting business idea and looks for funding, we'd be happy to fund anybody who's looking for applications within the realm of animation and self-supervised reinforcement learning for real physical problems or even non-real physical problems, such as, for example, financial markets. This is the Not Even Wrong podcast. It's September 1st, 2021. This is DALL.E. For the day, the fund is up 70 basis points. The market's flat. For the year, we're up 14%. The market is up 20.4%. We're underperforming by 6.4%. So ever since the Tesla AI day, a new door has opened up for us. It's something that's been lingering. And for all those who have been listening to this podcast, like I always say, the purpose of this podcast is to give people a sense for what it feels like to run a hedge fund. And this is a very good example of how you start gathering an idea and certain knowledge, and then every now and then it pops and you say, okay, this is what I'm looking for. This is exactly one of those situations. Here's the outline, here's the thesis, here's the idea. The idea is the following. We're looking for situations where the application of self-supervised reinforcement learning, or in short, self-learning, is enabling robots or generally AI systems to navigate in the real world. So we want to find situations where algorithms based on reinforcement learning enable self-learning and then solve problems in the spirit of AlphaGo Zero. Let me explain what AlphaGo Zero did. So AlphaGo Zero was developed by DeepMind, and it was the next step in their endeavor to build a system that can play Go. They started with AlphaGo, which was a system that played Go based on certain algorithms that were based on learning from humans. So those algorithms were watching humans play and learning from humans. So this was what's called behavioral cloning. And once those algorithms learned how to play from humans, they were then able to beat humans. What AlphaGo Zero did was learning by playing itself, using a certain what's called reinforcement learning algorithm, which in plain English just means you reward good moves and punish bad moves, and therefore get the system slowly towards an optimal solution. And according to David Silver, who was the lead research at DeepMind in the AlphaGo Zero endeavor, this system not just beat all the champions in AlphaGo, it also beat AlphaGo itself. So it beat the AI, which was based on behavioral cloning. And David Silver made a statement, which I think is just a very powerful statement. He said that I am making a scientific claim that the algorithm that we have every 5 years will beat the previous algorithm because there is more compute power available. And what he's trying to say here is that once you have this self-reinforcement learning algorithm and it's working, all you need is more iteration, which is another way to say we need more compute. Because in this context, compute is just iteration, iteration, iteration. And through iteration, you learn more and more moves, and therefore you get better and better and better. And what's really amazing about AlphaGo Zero is that AlphaGo Zero has developed strategies that humans never even thought about. And now this is where I want to transition now to self-driving, because I feel like self-driving has that same potential. First and foremost, it's a game played between cars and the rest of the world. It can be learned through self-supervised reinforcement learning. It's a very similar game. And I want to bring here also Wojciech Zaremba, who is the lead robotics researcher at OpenAI, who said that he thinks that self-driving cars is a very thankful application for robotics in the real world because it's all about avoiding obstacles. So you don't have to deal with the dexterity and the fine motor skills that are necessary, for example, for robot arms and things like that. So let's get now to our fundamental thesis here as far as self-driving technology is concerned. We are stating the following thesis, that we need a way to find a way to learn how to drive through self-learning. And there are two ways to do this. One is you build a robot that goes out in the wild and drives around and continuously crashes into things until the robot learns how to drive. Now, of course, this is not feasible. The second would be we need to find a way to simulate in an animated video what this robot does and then put it in the real world. Now, let's talk about simulation, because we are saying that in order to get to self-supervised reinforcement learning in the real world, first we have to solve the problem of video animation. What do I mean with that? Video animation has to be as real as possible, and it can only be real if the video animation itself is based on a deep learning AI system. In other words, the video animation itself has to learn and adapt to the real world. How can I do that? Well, one approach would be DALL.E. DALL.E is trying to do for video what GPT-3 is doing for text. GPT-3 is in the business of predicting the next word and has been shown to be incredibly successful when it comes to, for example, things like you prompt it, you say, this is a conversation with Elon Musk and Lex Friedman, and then GPT-3 can continue with this conversation, at least for a while, doing a very realistic conversation because it has learned over trillions of iterations what these two people represent and how they talk. The same idea is for DALL.E. DALL.E, this is the way I understand it, is a system where, let's say, you put a short prompt, let's say a video of a street in Zurich, and then the video starts predicting the next sequence and the next sequence. Sorry, DALL.E predicts that and builds a very realistic video of a street in Zurich. And then once that realistic video is available, the car, a virtual car, can learn through self-supervised reinforcement learning how to drive through Zurich, and therefore the algorithm can be tweaked in such a way that eventually it can be used in a real car and the real car can drive. This is the vision. This is the goal that we are setting out for ourselves, and this is what we hope Tesla will do. And we believe that Tesla will transition from the system that they have now to a self-learning system. In order to do that, Tesla needs to first solve the video animation problem. And again, it is absolutely crucial. I want to make sure we understand that video animation in this context means a system in the realm, in the spirit of GPT-3, which is DALL.E, something along those lines. Now, this can be done by Tesla itself, or it can be done by somebody like OpenAI, and then Tesla would adapt it. But what I'm saying here is that we first need to solve the video animation problem in order to allow self-supervised reinforcement learning for the real world. To finish, I want to also discuss a few other applications that we believe are very interesting. For example, we could have the same system. Let's say we could have a self-supervised reinforcement learning trading system that learns how to navigate the financial markets and generate wealth in the same realm where we have it go through trillions of iterations of financial markets and potential outcomes in financial markets, and then have the system become basically a virtual investor. This is incredibly orthogonal to what's happening right now, what all these algo traders are doing, because what all they're doing is they're using statistical information from the past and to try to bet on mean reversion. This is a very different system. This system, again, would learn from the behavior of trillions and trillions of iteration of financial markets, simulated financial markets, and through self-supervised reinforcement learning, gets better and better at generating wealth. Now, I am a little bit on thin ice here because I don't know exactly how these self-supervised reinforcement learning algorithms actually work. All I know is, like I said in the beginning of this episode, is it is a little bit like you reward the good stuff and you punish the bad stuff. But what it really means, what it really fundamentally means in terms of algorithmic implementation of the instantiation of, let's say, the actual algorithms, the mathematics behind it, I am not familiar with it. I think this is one of the areas where I'm going to have to educate myself and also try to meet researchers in the field and try to learn from them and see what is the state of the art and where can we go from here. So to summarize, this episode, the purpose of this episode is to lay down the foundations of what we believe is the future of physical AI systems. It is based on self-supervised reinforcement learning. And in order to do that, we need to solve the video animation problem, which in itself has to be based on a deep learning network. So that means the animation itself cannot be hard-coded. It has to learn from reality. So we use reality to train a system to animate reality, and then use that animated system, that video animation, to teach a robot through self-supervised reinforcement learning how to behave in reality. So we're kind of closing the loop here. We're going from reality to video animation to self-supervised reinforcement learning back to reality by implementing the algorithm that we've developed in self-supervised reinforcement learning and trained in the video animation, be using that algorithm as an inference tool for the actual robot that drives in the real world. This is the vision, and we're incredibly excited about this because we believe that Tesla is best positioned to do this. This is a clear line of sight of how we can actually get to what Elon Musk calls full self-driving. This is a realistic way to actually build robotaxis and all the things that right now seem almost too difficult to solve. We believe through self-supervised reinforcement learning, they can be solved. Just one example before I end this episode. Lex Friedman talks a lot about the game theoretic problems between pedestrians and cars. This is a very difficult problem to hard code or to solve in some sort of search algorithm. However, if we had trillions of iterations of a car through self-supervised reinforcement learning, learning how to navigate in a video animation where pedestrians are animated based on an AI that has learned from the real world, we will have a solution for that. This system will learn how to behave in this game theoretic way with the pedestrians, the same way AlphaGo Zero has been able to win in the game of Go by doing the right moves, by learning things that humans wouldn't have even come up with. And this is another absolutely important takeaway from AlphaGo Zero. The problem is, if we do behavioral cloning or any kind of hard coding or search algorithm or any of those things where we just basically have a more sophisticated expert system that is trying to solve problems, we are still biasing the system based on our human intuitions and knowledge. What AlphaGo Zero is doing is learning on its own to solve problems in ways that we humans can't even think about. Now, this translated to the self-driving car problem means that the self-driving car, once trained in this way, so through a video animation based on AI and then through self-supervised reinforcement learning, will learn how to drive in a much different way than we humans drive. I predict that over time, the system will, let's say, be able to avoid accidents way ahead of we humans could avoid accidents. For example, by seeing certain clues or understanding certain things that we humans don't even pick up on. Traffic patterns, weather patterns, things like that we don't even pick up on. So I predict that in the same spirit like AlphaGo Zero, that we will actually have creativity expressed through the system in a sense that it will do something new that we have never seen before because it's learning through self-learning. It is learning, it is in its own realm, in its own world, and its own world can be very different. This is very similar to, you take, let's say, a child and you put it through the school system, and you take another child and you let it self-learn. You will have very different outcomes in terms of how those two, let's say, adults, once they went through, let's say, they're 20 years old, how they solve problems, 100%. Now, one might be better than the other. I predict that the AlphaGo Zero approach will be better because, again, through computation, it will just have the luxury of trillions of iterations that humans don't have. But for one thing, I can make two statements here. One is any kind of algorithm that's based on self-supervised reinforcement learning will be different than an algorithm which is based on human behavioral cloning. And second, I will predict that with computational power attached with Moore's law going for it, that it will also be much better. Thank you.